Hi! We'll go through the last part of chapter 6 and 16, kinetics. So, from the experiment last week, we have calculated the rate of reaction, order of reaction, and reaction constant K. But what about the activation energy? We don't know how to calculate it so far, but that's what we're going to look at today. And for looking at activation energy, we use an equation called Arrhenius equation. So Arrhenius equation is the reaction constant equalized to frequency factor. We haven't looked at frequency factor so far. And the frequency factor is specific for each reaction, but it's not dependent on temperature. So if you run a reaction with different temperatures, the frequency factor will be the same. And we know E from mathematics. And we have activation energy, gas constant, and we have temperature. But what we want to calculate, what we want to look at today is the activation energy, which is now quite complicated. We have E in the power of minus activation energy divided by something. So that is quite complicated. And we can have a look down here. So we have done something with the equation. And now actually it's easier to calculate the activation energy. Now it's just divided by something. So we can have a look. How do we go from this equation up here to this equation down here? It doesn't look any less complicated, but actually it is, and we will look at that a little bit later. But first, how do we go from this equation to this equation? So we need to apply some logarithmic rules. We see that we have the natural logarithm and we have E. So we want to get rid of E. What we do is that we apply logarithms on both sides of the equation. Small k, sorry. So we have ln of the whole part of whole side of this equation minus EART. So this side we don't need to do anything more. So this is okay. Just write it again. And we apply logarithm rules, saying that if you multiply two things in a logarithm, you can separate them. I can use the parentheses as well. ln to E in minus activation energy, gas constant, and temperature. And now what we know next is that ln and E, they cancel each other. So we have the rate constant, frequency factor, and actually these two are canceling each other. We're left with a minus, plus and minus becomes minus. And we have activation energy, gas constant, and temperature. And now we can have a look. This is actually the same. We have ln k, we have ln to A, ln A, and we have minus activation energy, gas constant, and temperature. Perfect. So now we know how to go from this equation down to this one. What we want to calculate is the activation energy. But how do we do it? Actually, we have two different methods we can use. We are going to look at both of them, but we start with number one, which is graphically. So we can use a graph, because what is good with this equation, it's just the same as we had on the previous slide, is that if you look closely to it, you can see that it's actually a common equation for a graph, which meaning that y is equal to ln k. A, we set A to be equal minus activation energy over gas constant. X will be 1 over temperature. And B will be ln to the frequency factor. So actually on the x-axis here we have 1 over temperature. On the y-axis we have ln k. And if we now draw a linear line, the slope which is A, so the slope here will actually be, and we know that the slope is delta y over delta x, and that is A, which is actually equals to minus the activation energy over gas constant. And we have the interception between the line and the y-axis, which is B. And B is equal to ln A. So actually just from this plot, we can calculate everything we need to know in this reaction. We can calculate the frequency factor, and we can calculate the activation energy, as long as we know rate constant and temperature. We need to know temperature and rate constant. So we'll do one example. So we go into Excel. We have some known temperatures and some known rate constants. And remember that the rate constant changes if the temperature changes, as we can see they do. It's the same reaction, just run with different temperatures. So the first thing we do is that we calculate the temperature, or 1 over temperature. We do that for all of the values. And then we calculate ln to the rate constant. We write ln, click on the rate constant, and we do the same for all of the values. What we do now is that we want to plot. So we take these values and these values, and we want to plot them against each other. We press this dot diagram. And what we want to have now is that we want to make a trend line. So you click on these dots, you add a trend line, and what we want to do is that we want to have the formula as well. So show formula. So now we have made the plot. We can bring this, so we want to copy, and we bring this down here so we can do some calculations. Just a moment, we need to get it in here. Okay, it didn't want to join us. See one more time. There we go. Okay, so now we have the graph. We have this equation. If you do it by hand, you actually need to find this formula. So this will be the interception, where it crosses the y-axis. And see here that it doesn't go to 0 here, so actually we go a long way here. That's why it's 14. And the slope you need to calculate with taking the change in y-axis divided by the change in x-axis. But now we do it in Excel, so we go and get the formula automatically. So the task is to find the activation energy. So what is the activation energy? We know that this value here, this is A. So A, or minus activation energy over gas constant, are equal to minus 3378.9. Gas constant, that is, so we have minus and minus, those cancel out, and we multiply by R. Oh, I'm sorry, not up on both sides of the equation. Sorry. So these two cancel each other out, and we need to multiply on the other side too. So then we're left with only activation energy on this side. We have 3378.9 times the gas constant, and the gas constant, and actually the slope here have the value Kelvin, a unit Kelvin, and we times this by the gas constant, which is 8.314 joules Kelvin minus 1 and mole minus 1. So Kelvin and Kelvin in the power of minus 1 cancel each other out. We multiply these two together. So we have 3378.9 times 8.314, and that is 28092. 28092, which is in joules mole minus 1. We can redo into kilojoules. So we go 1, 2, 3, kilo means 1000. So 28.1 kilojoule mole in minus 1. And that is the activation energy for this reaction. So this was method number 1. For method number 2, you need to watch the next video.